September 2025. Multiple observatories, Hubble, ground-based telescopes, amateur networks, capture images of 3 Atlas, and in every image there's a feature that shouldn't exist. A tail pointing toward the sun, not away, toward Comet. Tails don't do that. They can't. Solar radiation pressure pushes particles outward at hundreds of meters per second. The solar wind, a stream of charged particles, blows outward at 400 kilometers per second. Every natural force says tails point away. Yet 3 Atlas has a sunward tail. Faint, persistent, real. So here's the question nobody in the scientific establishment wants to answer publicly. How? How do you make particles move against radiation pressure? How do you overcome the solar wind? And why would a natural comet need to? Dr. Raphael Ortiz, who models plasma dynamics around comets, ran simulations. His conclusion: if you wanted to create thrust using ice and dust, this is the configuration. Sunward jets, high-velocity particles, directional propulsion. In other words, if 3 Atlas were braking, slowing itself down as it approached Mars, as it approached Earth, this is exactly what you'd see. Retro rockets, made of ice, firing toward the sun. A quick request. Before we dive into the physics of the impossible, a small favor. If this investigation resonates with you, if you think these questions deserve answers, please hit the like button. It pushes this content to more people who care about the truth. Share your theory in the comments. Natural phenomenon or something more. And if you want to follow this story as it develops, subscribe and turn on notifications. This channel exists because of viewers like you. Your engagement makes the difference. Now, let's talk about tails that break the rules. Comet tails. 101. The rules before we can understand what makes 3 Atlas's anti-tail impossible. We need to establish what's normal. The 2 types of tails. Every active comet develops 2 distinct tails as it approaches the sun. The dust tail. Broad, curved, yellowish-white, composed of microscopic dust particles, silicates, organics, metal grains, released as ice sublimates from the nucleus. These particles scatter sunlight, creating the classic sweeping tail that can stretch for millions of kilometers. The ion tail, narrow, straight, electric blue, composed of ionized gas molecules, CO+, CO2+, H2O+, charged by ultraviolet radiation from the sun. The solar wind, a supersonic stream of protons and electrons, grabs these ions and accelerates them away from the sun at speeds exceeding 400 km/s. Both tails always point away from the sun, not behind the comet. Away from the sun. This is critical. A comet can be moving toward the sun, away from the sun, or sideways. Doesn't matter. The tails point away from the sun because the forces shaping them originate from the sun. Radiation pressure light carries momentum. When photons strike a dust particle, they transfer a tiny push. For microscopic particles, 1 to 10 microns across, this push is significant. At Earth's distance from the sun, 1 AU, radiation pressure accelerates dust particles outward at roughly 100 to 500 meters per second, depending on size and composition. Smaller particles feel more force relative to their mass. Larger particles feel less. But all particles feel outward push. This is why dust tails are curved. Particles released from the nucleus continue in the comet's orbital path while also being pushed outward by sunlight. The combination creates a graceful arc trailing behind and to the side. The solar wind. The solar wind is more than just light. It's a physical flow of plasma, ionized hydrogen and helium stripped from the sun's corona, streaming outward in all directions at supersonic speeds. At Earth's orbit, the solar wind moves at approximately 400 km/s. Near the sun, even faster. When the solar wind encounters a comet's coma, the cloud of gas and dust surrounding the nucleus, it creates a bow shock, similar to how a boat creates a wake in water. Magnetic field lines drape around the coma, and ionized gas is swept directly away from the Sun. This is why ion tails are straight. They're aligned with the interplanetary magnetic field embedded in the solar wind, pointing radially outward like a windsock. The inviolable rule: for 4.6 billion years, every comet observed has followed this rule. Tails point away from the Sun. Not usually, not most of the time. Always, until 3 Atlas. The anti-tail, observations, Hubble's images. In late September 2025, Hubble Space Telescope captured a series of high-resolution images of 3 Atlas in visible and near-ultraviolet wavelengths. The primary ion tail was there, streaming away from the Sun in classic fashion, blue, narrow, extending hundreds of thousands of kilometers into space. But there was something else, a faint, pale structure extending from the nucleus in the opposite direction, toward the Sun. Initial reports described it as possible dust lane, or asymmetric coma feature. Cautious language, because what the images actually showed was unambiguous, a secondary tail pointing sunward. Ground-based confirmation. Within days, amateur astronomers worldwide began posting their own images. Telescopes ranging from 8-inch backyard reflectors to 16-inch observatory-class instruments captured the same feature. One observer in Spain. At first I thought it was scattered light from the primary tail, but when I processed multiple frames, the structure is clearly separate. It extends sunward from the nucleus. Another in Chile. The anti-tail is faint, but it's there in every image. Different exposures, different filters. Same structure. Cross-referencing timestamps and viewing geometry, observers confirmed the anti-tail wasn't a perspective effect. It was real. Spectroscopic analysis. Spectroscopy reveals chemical composition and physical properties. When astronomers trained spectrographs on 3 Atlas's anti-tail, they found something surprising: large dust grains. The spectral signature matched particles at least 10 microns in diameter. Some estimates suggested 50 to 100 microns. These are boulders by dust standards, far larger and heavier than the typical 1-micron grains in normal dust tails. Why does size matter? Because radiation pressure's effectiveness decreases with particle mass. Larger grains require more force to move. For 10-micron grains to move sunward, against radiation pressure, they need to be launched with significant velocity, hundreds of meters per second, at minimum. That's not gentle outgassing. That's explosive ejection. The physics problem lets quantify the impossibility. Radiation pressure force at 2 AU from the Sun, 3 Atlas's approximate distance during observations. Solar radiation delivers about 340 watts per square meter. For a 10-micron silicate dust grain, radiation pressure exerts an outward force of approximately 10 to 12 newtons. Tiny. But for a particle with mass measured in nanograms, it's enough to accelerate it outward at roughly 200 meters per second over time. For particles to move sunward, they must overcome this force. That means they need to be launched with at least 200 ms velocity in the sunward direction, just to break even. To visibly extend sunward over hours and days, they need even higher velocities. The launch velocity problem. What mechanism launches dust grains at hundreds of meters per second? Normal outgassing. When ice sublimates, gas expands. This can carry dust particles along, but typical velocities are 10 to 50 ms. Not enough. Explosive outgassing. If subsurface pressure builds and releases suddenly, like a geyser, velocities can reach 100 to 200 nm. Still marginal. Hypervelocity jets. To launch 10-micron grains sunward with enough velocity to overcome radiation pressure and remain visible, you need sustained directed jets with velocities exceeding 300 ms. That's not typical cometary activity. That's extreme. The directionality problem. even if you could generate hypervelocity jets, why would they all point toward the Sun? Comets outgas from multiple vents across their surfaces. Some face sunward, some don't. The result is a diffuse coma and tails that average out to point away from the Sun. For an anti-tail to form, the outgassing must be concentrated on the sunward side. Only jets facing the Sun contribute to the anti-tail. Highly directional. Jets must fire in a narrow cone toward the Sun, not in random directions. Sustained. The anti-tail persists across days and weeks, meaning the jets are continuous, not sporadic. This level of organization doesn't happen by accident. The thrust hypothesis daughter. Raphael Ortiz, a plasma physicist at the Universidad Nacional de Córdoba, specializes in modeling comet-solar wind interactions. When he saw Hubble's images of the anti-tail, he did what any physicist would do. He ran simulations. The model Ortiz modeled a nucleus with asymmetric outgassing. Specifically, he simulated jets concentrated on the sunward hemisphere, firing with velocities of 300 to 500 ms input parameters. Nucleus size, 5 km diameter, upper estimate for 3 atlas. Jet velocity, 400 meters per particle size, 10 to 50 microns, gas composition. CO2 dominated, matching observed spectra, solar distance. 2. AU result. A sunward anti-tail, matching the observed structure. But here's what caught his attention: the net force. The reaction force, Newton's third law. For every action, there's an equal and opposite reaction. If 3I Atlas is ejecting material sunward at high velocity, the nucleus experiences a reaction force pushing it in the opposite direction, away from the Sun, retrograde. Ortiz calculated the thrust magnitude. Assuming continuous outgassing with the parameters above, the thrust would be on the order of several hundred newtons. That doesn't sound like much, but applied over days and weeks to a 5-kilometer nucleus with an estimated mass of trillions of kilograms, it's enough to produce measurable velocity changes. Changes like, say, a 10% deceleration as the comet approached Mars. Ortiz's conclusion, in a paper submitted to Icarus, still under review as of October 2025, Ortiz wrote, "The observed anti-tail structure is consistent with sustained, directional outgassing from the sunward hemisphere. If natural, this would represent the most asymmetric and energetic cometary activity ever recorded. Alternatively, if the outgassing is controlled, either by subsurface geometry or by active mechanisms, it could function as a propulsion system. The reaction thrust is sufficient to alter the comet's trajectory on timescales relevant to its solar system passage. Translation: this could be a rocket, and it's powerful enough to change the comet's course." Natural explanations. Do any fit? Let's systematically examine whether natural processes can account for the anti-tail. Hypothesis. 1. Viewing geometry. Illusion. Sometimes, when Earth crosses a comet's orbital plane, dust particles lying in that plane appear to extend both ahead and behind the nucleus, creating the illusion of an anti-tail. Problem. This effect is transient and depends on specific viewing angles. 3I Atlas's anti-tail persists across multiple observation dates and from different vantage points. Hubble in Earth orbit, ground-based telescopes at various latitudes. The geometry doesn't support an illusion. Hypothesis 2. Large grain. Survival. Maybe the anti-tail is composed of grains so large they're barely affected by radiation pressure, allowing them to drift sunward on residual orbital momentum. Problem. Large grains don't drift sunward. They continue along the comet's orbital path. For grains to visibly extend toward the Sun, they need active propulsion. Passive particles wouldn't form a directed structure. Hypothesis. 3. Asymmetric nucleus. Shape, perhaps the nucleus has an irregular shape that focuses outgassing toward the Sun, like a nozzle. Problem: while plausible in principle, this requires an extraordinary coincidence. The nucleus would need to be shaped such that jets naturally concentrate sunward, remain stable as the comet rotates, or 22 hours per rotation, and sustain this configuration for weeks. Possible? Barely. Likely? No. Hypothesis. 4. Subsurface chambers. Maybe there are subsurface voids filled with volatile ice. When heated, pressure builds until the surface ruptures, launching material explosively. Problem: this can produce high-velocity jets, but why would all the active vents be on the sunward side? And why would they fire continuously? Explosive vents typically erupt, exhaust, and then go dormant. Sustained outgassing requires sustained heat input and structural stability, difficult to achieve naturally with the required directionality. Hypothesis. 5. Electromagnetic. Acceleration could electric or magnetic fields. Accelerate charged dust grains sunward. Problem: comets don't generate strong intrinsic magnetic fields. And even if they did, accelerating neutral dust grains requires the particles to be charged and the fields to be configured in a very specific way. There's no evidence for this in 3I Atlas's environment. The uncomfortable conclusion. Every natural explanation requires special conditions, unlikely geometries, or unprecedented activity. Individually, each is marginally possible. Together, the probability drops precipitously. The simplest explanation, the one that requires the fewest assumptions, is that 3I Atlasis actively directing outgassing for propulsion. Retro rockets made of islets entertain the hypothesis seriously. If 3I Atlas is using outgassing for thrust, how would it work? Spacecraft propulsion. Basics: all rockets work on the same principle. Eject mass in one direction. Move in the opposite direction. Chemical rockets burn fuel, creating high-pressure gas that exits through a nozzle at high velocity. Ion drives accelerate charged particles with electric fields. Solar sails reflect photons. All achieve thrust by expelling something. Comet-based propulsion. If you're traveling through interstellar space and you need to adjust your trajectory, but you don't have chemical fuel or solar panels, what do you have? Ice. Lots of ice. Specifically, 3I Atlas is rich in carbon dioxide ice. CO2 sublimates at much lower temperatures than water ice, around -78 Richters at low pressure. As the comet approaches the Sun, solar heating naturally vaporizes CO2. If you could channel that gas through vents positioned on the sunward side of the nucleus, you'd create thrust. The escaping gas pushes sunward. The comet reacts by accelerating retrograde, away from the Sun. That's a braking maneuver. The engineering challenge for this to work: you need controlled venting. Jets must fire from specific locations, not randomly across the surface. Thermal management. Subsurface ice reservoirs need to sublimate at controlled rates. Structural integrity. The nucleus must withstand the internal pressures without fracturing chaotically. This isn't trivial, but it's not magic. It's engineering. If 3I Atlas were designed, sent by a civilization capable of interstellar travel, using ice as propellant is elegant. The fuel is built into the structure. No need for separate tanks or engines. Just carefully positioned vents and subsurface channels directing gas flow. The deceleration connection, recall, 3. Atlas decelerated by approximately 10% as it approached Mars. We covered this in a previous video. No natural explanation fit. But if the anti-tail represents active thrust, the deceleration makes perfect sense. Fire retro rockets continuously for weeks. Slow down from 72 km to 68 km. Adjust velocity for a close Mars flyby. The anti-tail isn't just a weird feature. It's evidence of propulsion. The data gaps and institutional silence. So, where's the official analysis? No published papers as of October 2025. No peer-reviewed paper has been published analyzing 3I Atlas's anti-tail. Ortiz's submission to Icarus remains under review. Informal reports circulate on preprint servers, but mainstream journals haven't touched it. Amateur observations are documented on forums and personal blogs. But institutional acknowledgement? Absent. The NASA non-statement in response to inquiries from independent researchers, NASA's Planetary Science Division issued a brief statement. Asymmetric outgassing and dust structures are observed in many comets. Further analysis of 3I Atlas's activity is ongoing. No mention of the anti-tail specifically. No discussion of thrust implications. Generic language. Why the silence? Publishing a paper that says, "This comet appears to be using directed outgassing for propulsion," invites catastrophic scrutiny. If you're wrong, your career is damaged. If you're right, you've just told the world that an interstellar object might be artificial. That opens a door institutions aren't ready to walk through, so they stay quiet. They gather more data. They debate privately, and in the meantime, the anti-tail continues. The thrust continues. The deceleration continues. Conclusion: the Sunward streak, September 2025. Hubble, ground-based telescopes, amateur networks, all capture the same impossible feature: a tail pointing toward the sun. Comet tails don't do that. Physics says they can't. Radiation pressure pushes outward. Solar wind blows outward. Every force says tails point away. Yet there it is. Faint, persistent, real. Dr. Raphael Ortiz ran the simulations. The anti-tail matches sustained, directional jets, high-velocity particles, concentrated on the sunward side, and the thrust. Enough to slow a comet by 10%, enough to adjust a trajectory, enough to brake before reaching Mars. Every natural explanation requires unlikely coincidences, asymmetric shapes, explosive vents, perfect geometry. The simplest answer: 3I Atlas is firing retro rockets, made of ice, controlled, directed, deliberate. Subscribe to Narrator of Shadows. Because when a comet breaks the rules of physics, we need to ask what rules it's actually following. The anti-tail is there. The thrust is real, and something inside that icy nucleus is pointing its exhaust toward the sun. For a reason.